What if everything you thought you knew about the universe was just the tip of an iceberg, one hiding layers of contradictions so strange they make the impossible seem real? Picture a cosmic dance where black holes swallow information whole, where time itself can twist into loops, and where the vacuum of empty space crackles with infinite energy. These aren't plot twists from a sci-fi novel. They're real paradoxes etched into the fabric of our universe, waiting to unravel the very foundations of physics as we know it. Astrophysics is a field built on discovery, but every so often, it stumbles upon something so baffling, so beautifully illogical, that it forces us to question everything. Take the Fermi Paradox, for instance. If the universe is teeming with potential for life, why does the cosmos feel so silent? Or consider the black hole information paradox, where the rules of quantum mechanics and gravity clash in a battle with no clear winner. These aren't just academic puzzles, they're cosmic mysteries that reveal how much we still don't understand, no matter how advanced our telescopes or equations become. Today, we're diving deep into 29 of the most mind-bending paradoxes that exist in real astrophysics, each one a doorway into the universe's best-kept secrets. Some will make you question reality itself, while others might leave you marveling at how something so counterintuitive could be true. But one thing's for certain, by the end of this journey, you'll see the cosmos in a whole new light, one where the impossible isn't just possible, but inevitable. So buckle up, the universe is stranger than you ever imagined, and we're just getting started. The silence of the universe might be the loudest mystery of all. With billions of galaxies, each containing billions of stars and planets, the math suggests life should be everywhere, yet we hear nothing. This eerie quiet is the heart of the Fermi Paradox, a puzzle that gnaws at the very foundations of our cosmic assumptions. One explanation is the Great Filter, a hypothetical barrier that prevents life from advancing beyond a certain point. Maybe it's the rarity of life forming in the first place, or perhaps civilizations inevitably hit a wall. Climate collapse, nuclear war, or runaway AI that wipes them out before they can spread across the stars. If that's true, the haunting question becomes, have we already passed the filter, or is it still looming in our future? Then there's the zoo hypothesis, the idea that advanced civilizations are out there but deliberately avoiding contact, treating Earth like some kind of cosmic nature preserve. Imagine a universe where we're the ones being observed, like ants in an interstellar terrarium, left undisturbed until we're deemed ready. Or maybe alien communication is so advanced it's unrecognizable, like trying to decipher radio waves with a stone tablet. But here's the twist that chills the spine. What if the silence isn't about them at all? What if the universe is fundamentally hostile to long-lived civilizations, wiping them out with gamma-ray bursts, asteroid impacts, or some unseen cosmic force we haven't even discovered yet? The Fermi Paradox doesn't just ask where the aliens are, it forces us to confront whether intelligence itself is a fleeting spark in the dark, doomed to flicker out before it can light up the cosmos. Black holes are the universe's ultimate vault, swallowing stars, light, and even time itself, locking everything away behind an event horizon where nothing can escape. But here's the cosmic conundrum. According to quantum mechanics, information can never truly vanish. It might get scrambled or hidden, but it's always preserved, like a cosmic ledger keeping track of every particle's past. Yet black holes seem to break this rule, erasing information as if it never existed. This clash between quantum theory and Einstein's relativity is the black hole information paradox, and it's one of the fiercest battles in modern physics. Stephen Hawking threw the first punch in this debate when he discovered that black holes aren't entirely black. They slowly leak energy, what we now call Hawking radiation, and over eons they evaporate entirely. But here's the problem. That radiation appears random, carrying no trace of the information swallowed by the black hole. It's like burning a library and claiming the smoke particles still hold the stories from every book. If the information is truly lost, it shatters quantum mechanics. If it's preserved, we have no idea how. Some theorists argue the answer lies on the event horizon itself. The holographic principle suggests that all the information sucked into a black hole isn't destroyed but smeared across its surface, like a cosmic fingerprint encoded in 2 dimensions. Imagine stepping into a black hole and finding the entire history of everything it's ever consumed etched onto its boundary, a hologram of reality itself. Others propose that information escapes through subtle quantum connections in the radiation, hidden in patterns too complex for us to decipher yet, but the most mind-bending idea. That black holes might not be the end at all. Some models suggest they could birth new universes, with the information reborn in a big bang on the other side. Picture a black hole as a cosmic tunnel, not a dead end, a place where the laws of physics rewrite themselves entirely. Until we solve this paradox, black holes remain the ultimate riddle, forcing us to question whether our theories of reality are incomplete or if the universe is far stranger than we ever dared to dream. Look up at the night sky and you'll see darkness punctuated by pinpricks of light, but here's what's strange. If the universe were truly infinite, eternal, and packed with stars, every point in that sky should blaze with the brightness of a sun. This is Olbers Paradox, a question that troubled astronomers centuries ago and still makes us rethink the nature of the cosmos. At first glance, the math seems undeniable. In an infinite universe, no matter which direction you gaze, your line of sight should eventually land on a star. Even if distant stars appear faint, their sheer numbers would stack up, flooding the night with relentless light. So why isn't the sky a solid wall of white? The answer cracks open 2 astonishing truths about our universe. First, the universe isn't static, it's expanding. As space stretches, light from the most distant stars gets stretched too, shifting toward longer, redder wavelengths. Eventually, this light red shifts so much it slips beyond the visible spectrum, fading into darkness like a cosmic whisper we can no longer hear. The second revelation: the universe has a finite age. Light from stars beyond a certain distance simply hasn't had time to reach us yet. We're not seeing the full cosmic tapestry because the threads are still weaving themselves into place. But the implications go even deeper. Olbers Paradox hints that the universe had a beginning, a moment when everything burst into existence. Without that starting point, starlight would have had infinite time to fill the sky, leaving no patch of darkness untouched. It's a paradox that quietly reshaped cosmology, proving that even the simplest observations can unravel the grandest mysteries. And here's the twist: the darkness above isn't just empty space. It's a cosmic fossil, a snapshot of a universe too young and too dynamic to ever show us all its light. Every time you look up at the night sky, you're not just seeing stars, you're seeing the limits of time itself. Imagine saying goodbye to your identical twin, watching them blast off on a spaceship traveling close to the speed of light, only to reunite decades later and find them still young while you've aged into retirement. This isn't science fiction, it's the twin paradox, one of the most startling predictions of Einstein's theory of relativity. At first glance, it seems like a symmetrical swap. From the traveling twin's perspective, shouldn't Earth appear to move away at near light speed, making you the one who ages slower? But reality isn't so fair. The key lies in a detail often overlooked: acceleration. While both twins start in the same reference frame, only the astronaut twin feels the crushing force of the ship's engines firing, the stomach-dropping turns, and the deceleration upon return. These moments of acceleration break the symmetry, proving their journey isn't just a matter of relative motion. General relativity steps in here, revealing that gravity and acceleration warp time itself. The traveling twins path through space-time bends, shortening their experience of time compared to the one who stayed home. It's as if the universe keeps a ledger, and acceleration stamps an undeniable receipt. This paradox isn't just a clever puzzle, it's been tested. Atomic clocks flown on high-speed jets tick slightly slower than those on the ground, and GPS satellites must account for relativity's time warps to keep our maps accurate. Even a fraction of a second adds up over years, just like the twin who returns to find their sibling has lived a lifetime in their absence. But the real mind bender isn't the math, it's what this says about time. There's no universal clock ticking away in the background. Time stretches and compresses like taffy, depending on how you move and where you are. The twin paradox shatters our everyday intuition, forcing us to accept that time isn't a river flowing at the same speed for everyone. It's a mosaic fractured by motion and gravity, where your personal slice of reality might be wildly different from someone else's. So next time you glance at a clock, remember, it's not just measuring minutes. It's measuring your path through a universe where time itself is negotiable. What if the greatest novel ever written had no author, not because it was lost to history, but because it was never created in the first place? That's the heart of the Bootstrap Paradox, a cosmic riddle where cause and effect twist into an endless loop with no beginning. Picture a time traveler handing Beethoven a symphony they claim is his own masterpiece. He copies it note for note, publishing it as his work, but who truly composed it? The music has no origin, no moment of creation. It simply exists, trapped in a cycle where the future writes the past. In astrophysics, this isn't just a thought experiment. Closed time-like curves, theoretical pathways where space-time bends back on itself, could allow events to become their own cause. Imagine a planet where the same storm has been raging for eternity, its lightning strikes powering the very conditions that birth it, or a star whose explosion sends ripples backward in time, triggering the collapse that created it. These loops defy our understanding of causality, making the universe feel less like a straight timeline and more like a Möbius strip of reality. Quantum mechanics might offer an escape hatch. Some interpretations suggest that probability waves would self-correct to prevent paradoxes, like a cosmic editor snipping away inconsistencies. Others argue that every paradox spawns a parallel timeline, branching realities where each possibility plays out. But the most unsettling idea, that the universe doesn't care about origins at all. If time isn't linear but a tangled web, then the Bootstrap Paradox isn't a flaw, it's a feature, revealing a cosmos where creation isn't a moment but a mosaic of infinite echoes. This paradox doesn't just challenge time travel, it forces us to ask whether first causes are illusions. What if every discovery, every invention, is just a relic from a future that hasn't happened yet? The Bootstrap Paradox doesn't just bend time, it erases the line between creator and creation, leaving us to wonder if we're writing history or merely rewriting it. The cosmos seems to be racing toward an inevitable, frozen demise, a state where every star burns out, every particle drifts endlessly apart, and the universe becomes a lifeless void. This is the heat death, the ultimate victory of entropy as predicted by the second law of thermodynamics. Yet here we are, surrounded by galaxies, planets, and even life itself, all defying the odds in a universe supposedly sliding into chaos. How can complexity thrive in a reality destined for disorder? That's the heat-death paradox, a contradiction that forces us to rethink the very nature of time and existence. Gravity might be the unsung hero in this cosmic struggle. While entropy pushes systems toward randomness, gravity pulls matter together, forging stars from dust and sculpting galaxies from clouds of gas. It's as if the universe has two opposing forces locked in an eternal tug of war, one scattering energy into oblivion, the other clustering it into pockets of breathtaking order. Think of a whirlpool in a river. The water around it flows toward entropy, but the vortex itself is a temporary masterpiece of structure. Could the universe be filled with similar eddies, where gravity holds entropy at bay just long enough for life to emerge? But gravity alone might not explain the delay. Some cosmologists speculate that dark energy, the mysterious force accelerating the expansion of the universe, could be buying time for complexity to flourish. Others propose even wilder ideas, like cyclical universes that collapse and rebirth endlessly, or quantum fluctuations that reset the cosmic clock. Imagine a phoenix universe where each heat death is merely the prelude to a new Big Bang, erasing the slate clean for another cycle of creation. The most radical solution, that entropy isn't the full story. Quantum mechanics hints at strange loopholes, regions where time's arrow might not point so rigidly toward decay. If true, the universe's fate might not be a cold, dark surrender, but a transformation into something we can't yet imagine. The heat-death paradox doesn't just question our future, it challenges whether we truly understand the rules of the game. After all, if the universe were truly doomed to uniformity, how did we get here to wonder about it in the first place? Galaxies spin like cosmic carousels, their outer stars whipping around so fast they should fling into the void, yet something invisible holds them together. This cosmic glue we call dark matter makes up 85% of the universe's mass, bending space-time like an unseen hand. But here's the catch. After decades of hunting with ultra-sensitive detectors buried deep underground in Antarctic ice and even in space, we've never directly caught a single particle of it. The dark matter paradox forces us to confront a humbling truth. Either our tools are too blunt, or our understanding of gravity is fundamentally flawed. Enter modified Newtonian dynamics, a daring idea that suggests gravity behaves differently at galactic scales than in our solar system. Picture a playground merry-go-round, push it gently, and Newton's laws predict how fast it spins. But if unseen kids were secretly pushing too, you'd assume an invisible force. Mund argues there's no need for dark matter. Instead, gravity itself strengthens slightly where accelerations are tiny, like in a galaxy's faint outskirts. It's an elegant fix until you realize galaxy clusters and cosmic web structures still demand extra mass to hold together. Mund stumbles where dark matter strides, leaving scientists torn between two incomplete theories. The stakes couldn't be higher. If dark matter exists but evades detection, it might be stranger than we dreamed, perhaps interacting only via gravity, making it a cosmic ghost. Some experiments hunt for hypothetical WIMP, weakly interacting massive particles, while others probe for actions, particles so light they behave more like waves. Yet every empty result fuels the fire for alternatives, like primordial black holes forged in the Big Bang's first seconds, lurking unseen in galactic halos. But the boldest twist, dark matter might not be matter at all. Quantum fields or extra dimensions could warp gravity in ways that mimic invisible mass. Imagine the universe as a trampoline. Visible matter are the bowling balls you see, but hidden springs beneath the fabric could create dips that look like extra weight. This paradox isn't just about missing mass, it's a crack in the foundation of physics, revealing how much of the universe's blueprint we're still decoding. Every galaxy rotation curve, every gravitational lens bending light whispers the same question. Are we hunting shadows, or is reality far more malleable than we ever suspected? The quantum world operates on rules so bizarre they make everyday logic seem dull by comparison. Take a single electron. Until you measure it, it doesn't have a definite position or spin. It exists as a blur of probabilities, a superposition of all possible states at once. But the moment you observe it, this fuzzy cloud collapses into a single, concrete reality. This is the quantum measurement paradox, a puzzle so deep it forces us to ask, does reality even exist when we're not looking? Schrödinger's cat is the poster child of this conundrum. Imagine a feline locked in a box with a vial of poison triggered by a quantum event, say, the decay of a radioactive atom. Until you open the box, the atom is both decayed and not decayed, and the cat is simultaneously alive and dead. It's not just a metaphor, it's a stark illustration of how quantum mechanics defies common sense. The act of observation seems to force the universe to pick a side, as if reality itself hesitates until we intervene. But who or what counts as an observer? The Copenhagen interpretation, championed by Niels Bohr, suggests the wave function collapses when a measurement is made by a classical system, like a human or a detector. It's a clean division between the quantum and the everyday, but it leaves a glaring question. Where exactly does that boundary lie? Is a camera observing the cat enough, or does it require a conscious mind to seal the deal? This ambiguity led to wilder ideas, like the von Neumann-Wigner interpretation, which posits that consciousness itself is the trigger, a notion that blurs the line between physics and philosophy. Then there's the many worlds interpretation, which sidesteps the paradox entirely by declaring that every possible outcome happens, just in alternate branches of reality. In this view, the cat never collapses into a single state. Instead, the universe splits, spawning one timeline where it purrs and another where it perishes. No observer is needed because every possibility plays out somewhere, turning the cosmos into an infinite tapestry of parallel realities. But not everyone buys into branching universes or conscious observers. Objective collapse models, like the Garadi-Rimini-Weber theory, propose that wave functions collapse spontaneously due to tiny, inherent instabilities in the system. Picture a house of cards trembling until it inevitably falls. No one needs to touch it. These models suggest quantum weirdness has a built-in expiration date, a cosmic failsafe that prevents superpositions from scaling up to absurdity. At its core, the quantum measurement paradox isn't just about electrons or hypothetical cats. It's a challenge to our understanding of reality itself. Does the universe exist independently, or do we somehow co-author it through observation? Quantum mechanics offers no easy answers, only a dizzying array of possibilities, each more mind-bending than the last. And perhaps that's the most unsettling truth of all. In the quantum realm, the act of seeking answers might just change what those answers are. What if the key to your existence lay in your own hands, or rather, in your ability to resist using them? The grandfather paradox isn't just a time traveler's nightmare. It's a razor slicing through our assumptions about reality. Picture this: you journey back to the past and prevent your grandparents from meeting. No grandparents, no parents know you. But if you never existed, who traveled back to disrupt their meeting in the first place? This dizzying loop isn't just a plot hole in sci-fi. It's a genuine crisis for physics, forcing us to ask whether the past is set in stone or if causality itself can unravel. One escape route comes from self-correcting timelines where the universe plays referee. Imagine trying to erase your own birth only to find fate conspiring against you. a missed train, a sudden storm, or a slip on a banana peel preserving the timeline like a cosmic joke. This Novikov self-consistency principle suggests that any actions taken in the past were always part of history, woven seamlessly into the fabric of events. Your attempt to meddle might be the very reason things unfolded as they did. It's a comforting idea, time as an unbreakable chain where free will is an illusion and every choice was inevitable. But what if time isn't a single thread but a frayed rope? The multiverse theory offers a wilder solution. Every decision spawns a new universe. Kill your grandfather and you don't vanish. You simply branch into a reality where you were never born, while the original timeline chugs on without you. In this view, paradoxes aren't problems, they're just forks in an infinite road. Quantum mechanics even lends credence to this idea, with experiments showing particles existing in multiple states until observed. Could entire history split the same way? Then there's the observer's gambit, the notion that time travel might only let you witness the past, not touch it. Like a ghost drifting through history, you'd see events unfold but lack the power to alter them. This block universe model treats time as a frozen landscape, every moment, past and future, already set like frames in a film reel. You're not rewriting the script, you're just hopping between scenes, but the boldest twist comes from quantum mechanics itself. Some theories suggest closed time-like curves, loops in space-time, could allow time travel without paradoxes, as quantum probabilities naturally resolve contradictions. It's as if the universe has a built-in undo button, tweaking reality just enough to keep the math tidy. The grandfather paradox doesn't just question time travel, it forces us to confront whether the past is a story we're reading or one we're writing. Are we prisoners of causality, or is the universe more flexible than we dare to believe? Either way, one thing's certain. The answer lies somewhere between the impossible and the inevitable. Imagine waking up one day as nothing more than a lone, disembodied brain, floating in the void of space, no body, no earth, no stars, just raw consciousness blinking into existence from pure cosmic chaos. This unsettling thought experiment is the heart of the Boltzmann brain paradox, a puzzle so strange it makes solipsism seem tame. The idea comes from Ludwig Boltzmann's work on thermodynamics, which suggests that in an infinite universe, random fluctuations could spontaneously create complex structures, even self-aware ones given enough time. If that's true, why are we here, embedded in a vast, ordered cosmos instead of being fleeting anomalies, momentary glitches in the cold expanse of nothingness? The paradox cuts deep because it pits probability against perception. Statistically, a single, isolated brain popping into existence from quantum noise is infinitely more likely than the emergence of an entire universe with galaxies, planets, and billions of years of history. Think of it like shuffling a deck of cards. Getting one specific card is easy, but getting a perfectly ordered sequence is astronomically rare. So why does our reality feel so meticulously structured? Some physicists dismiss the idea as philosophical nonsense, arguing that a Boltzmann brain wouldn't have consistent memories or a stable sense of time. It'd be a brief, fragmented consciousness with no way to verify its own existence. But others take it seriously, seeing it as a glaring flaw in our understanding of cosmology. One way out is the anthropic principle. We observe an ordered universe because only such a universe could support observers like us. In other words, the very fact that we're here to ponder the question means we must be part of a stable, long-lasting reality. But this feels like a cosmic cheat, a shrug disguised as an answer. Another escape route involves inflation theory. The idea that our universe's rapid expansion in its earliest moments set the stage for large-scale structure, making Boltzmann brains far less likely than the world we see. Yet even this doesn't fully resolve the tension. If the multiverse is real, with infinite pocket universes bubbling into existence, there's still a non-zero chance that one of them, or one of us, is just a statistical fluke. The most unsettling implication isn't just about probability, it's about identity. If Boltzmann brains are possible, how do we know we're not one of them? Could our memories, our sense of history, even this moment right now, be an illusion conjured by random quantum flickers? It's a modern twist on Descartes' evil demon, replacing philosophy with physics. The paradox doesn't just challenge our models of the universe, it undermines the very ground of subjective experience, leaving us to wonder whether reality is a cosmic accident or something deeper. And perhaps that's the point. In a universe where the impossible is statistically inevitable, the only certainty is the mystery itself. What if the very fabric of empty space wasn't empty at all, but teeming with particles that only reveal themselves to someone moving in just the right way? This is the Unruh Effect, a paradox so counterintuitive it makes the vacuum of space seem like a cosmic magic trick. Picture two observers, one floating peacefully in deep space, the other strapped into a rocket accelerating at breakneck speeds. To the first, the universe is a silent void, utterly devoid of particles. But to the second, that same emptiness crackles with heat, a bath of warm radiation popping into existence simply because they're moving faster and faster. How can two people experience the same patch of nothingness so differently? The answer lies in one of quantum mechanics' strangest quirks. Particles aren't permanent fixtures of reality. Instead, they're fleeting disturbances in quantum fields, flickering in and out of existence. Normally, these disturbances cancel each other out, leaving empty space truly empty. But acceleration changes the rules. For the observer in the rocket, the act of speeding up warps their perception of these quantum ripples, stretching some vibrations into what looks and feels like real particles. It's as if the universe has a secret rulebook, one where motion rewrites the definition of nothing. This effect isn't just theoretical. It's deeply tied to Hawking radiation, the eerie glow that black holes emit as they slowly evaporate. Near a black hole's event horizon, gravity is so intense it mimics acceleration, conjuring particles from the void in the same way the Unruh Effect does. Both phenomena hint that reality isn't as fixed as we thought, that what we call empty depends entirely on how we're moving through it. But here's where the paradox bites hardest. If particles can appear or disappear based on motion, does objective reality even exist? Or is the universe a shape-shifting illusion, revealing different truths to different observers? The Unruh Effect doesn't just challenge our ideas about space, it forces us to ask whether the cosmos is a stage where every observer gets their own private performance. And if that's true, how do we know which version of reality, if any, is the real one? Empty space should be anything but empty, at least according to quantum physics. The vacuum of space isn't just a void. It's a seething ocean of virtual particles popping in and out of existence, a quantum froth so energetic it should make the cosmos explode with unimaginable force. But when we look out at the universe, we see none of that chaos. Instead, the vacuum energy is eerily calm, almost zero. This jaw-dropping mismatch, where theory predicts a number 10 raised to the power of 120 times larger than what we observe, is the vacuum catastrophe, the most embarrassing failure of modern physics. At the heart of this paradox lies a simple but devastating calculation. Every quantum field, from electromagnetism to the Higgs field, fluctuates constantly, contributing tiny amounts of energy to the vacuum. Add them all up, and the result should be a cosmic energy density so colossal it would warp space-time beyond recognition, tearing galaxies apart before they could even form. Yet reality laughs at this prediction. the universe expands at a leisurely pace, with a vacuum energy so small it's as if all those quantum fireworks cancel each other out perfectly. One possibility is that we're missing a hidden symmetry, a secret law of nature that forces positive and negative contributions to balance to near zero. Think of it like a cosmic accountant, meticulously adjusting the books so every debit has a matching credit. Supersymmetry, a beloved but still unproven theory, once promised such a solution, but so far, particle colliders have found no trace of the required superpartner particles. Another idea is that vacuum energy isn't static but dynamic, evolving over time like a dial being fine-tuned by some unknown mechanism. Imagine the early universe boiling with energy, then cooling to its current whisper as space expanded, leaving behind just a faint echo. But the most radical solution is also the simplest. Maybe we're calculating it all wrong. Quantum field theory works stunningly well for particle physics, but applying it to the entire cosmos might be like using a microscope to map a continent. Cosmology operates on scales where gravity dominates, and our theories of quantum gravity like string theory or loop quantum gravity remain incomplete. Could the vacuum catastrophe be a clue that we're stitching the fabric of reality together with the wrong thread? The stakes here are cosmic. If vacuum energy were even slightly larger, galaxies would never have clumped together. If it were negative, the universe would have collapsed in on itself eons ago. The fact that we exist to measure it at all suggests something extraordinary. Either an undiscovered principle is at work, or our understanding of nothingness is fundamentally broken. The vacuum catastrophe isn't just a gap in our knowledge. It's a screaming reminder that the universe still holds its deepest secrets close, and until we solve it, we're left staring into the void, wondering why it stares back so quietly. Imagine a civilization so advanced, it harnesses the entire energy output of its star, encasing it in a vast, intricate web of solar collectors known as a Dyson sphere. Such a structure would glow not with visible light, but with the infrared warmth of waste heat radiating into space. For decades, scientists have scanned the cosmos for these telltale thermal fingerprints, expecting to find evidence of cosmic engineers at work. Yet the skies remain silent. This is the Dyson sphere paradox. If intelligent life evolves to master stellar energy, why does the universe seem devoid of these colossal power plants? One explanation is that we're searching for the wrong signs. A civilization capable of building a Dyson sphere might have moved beyond crude infrared signatures, perhaps recycling waste heat with near-perfect efficiency or tapping into dark energy itself. Picture an ant searching for humans by looking for campfires, missing the skyscrapers and power grids right above it. Our assumptions about alien technology could be hopelessly primitive, like trying to spot a stealth jet with a candle. Then there's the possibility that megastructures are rarer than we think. Constructing a Dyson sphere requires dismantling planets, manipulating asteroids on an unimaginable scale, and maintaining stability across billions of miles. Even for an advanced species, the energy and resources needed might outweigh the benefits. Why cage a star when zero-point energy or black hole engines could offer cleaner, more portable power? The universe might be full of civilizations that skip the Dyson sphere phase entirely, leaping straight to energy sources we can't yet fathom. But the most haunting answer is that they're hiding. A civilization wary of predators or of becoming one might deliberately cloak its presence, masking heat signatures or redirecting energy in ways invisible to our telescopes. The same logic that makes us cautious about broadcasting radio signals could apply to stellar engineering. In a dark forest universe, the smartest species might be the ones we never see. The Dyson sphere paradox doesn't just challenge our search for aliens, it forces us to question the very trajectory of intelligence. Are megastructures inevitable markers of progress, or just a fleeting phase in a civilization's evolution? Until we find an answer, every unexplained infrared signal remains a tantalizing maybe, a shadow on the cave wall of the cosmos, hinting at wonders we've yet to understand. What if every star, every atom, every thought you've ever had was nothing more than lines of code in an unfathomably advanced simulation? The simulation paradox doesn't just ask whether we're living in a virtual world, it forces us to confront why we'd even be allowed to suspect it. If future civilizations can create hyper-realistic simulations, the math seems undeniable. There'd be countless simulated universes for every real one, making it statistically likely we're just digits in someone else's cosmic computer. But here's the twist: if we're mere simulations, why would our creators program us to question our own reality? This paradox splits thinkers into two camps. One side argues that the very fact we're pondering this question is proof we're in base reality, the original universe where simulations are born. After all, why would a simulation contain glitches big enough to reveal its own artificiality? It'd be like a video game character suddenly realizing it's made of pixels and shouting through the screen at the player. Any civilization capable of building such a perfect simulation would surely patch out existential doubts, leaving its creations blissfully unaware. Yet others propose a far stranger possibility, that uncovering the truth might be the point. Imagine simulations stacked like Russian dolls, each one running its own nested realities, all governed by hidden rules. Our universe could be an experiment, an art project, or even a training ground for fledgling gods. In this scenario, discovering we're simulated isn't a bug, it's a rite of passage, a test to see if we're ready to ascend to the next layer. Think of it like a character in a novel realizing they're in a story, then wrestling with the implications of who's holding the pen, the most unsettling version. That we're not just in a simulation but a failed one. Glitches in quantum mechanics, like the observer effect or entanglement, could be artifacts of imperfect rendering cosmic lag in a universe still buffering. Even the speed of light might be nothing more than a processing limit, a firewall preventing us from overloading the system. And if that's true, the real question isn't whether we're simulated but how long until the servers crash. But here's the kicker: even if we prove we're in a simulation, it changes nothing about how we experience reality. Your joy, your pain, the starlight brushing your eyes, all of it feels real because to you it is real. The simulation paradox doesn't just blur the line between illusion and truth. It reminds us that meaning isn't handed down by creators. It's something we build ourselves, one moment at a time, whether we're made of atoms or algorithms. So the next time you gaze at the night sky, wonder not just if it's code but why it moves you anyway. At the heart of every black hole lies a cosmic impossibility, a point of infinite density where the laws of physics simply stop making sense. This is the singularity, a place where gravity becomes so intense that space and time curve beyond recognition. Equations spit out infinities, and our understanding of reality hits a wall. But here's the problem: infinities don't exist in nature. Everywhere else we look, from the smallest quantum flicker to the largest galaxy, the universe operates within finite, measurable bounds. So why does general relativity, our most robust theory of gravity, predict these absurd breakdowns? The Singularity Paradox isn't just a quirk of math, it's a screaming siren that Einstein's masterpiece is incomplete. Quantum mechanics might hold the key to this cosmic lock, while general relativity treats space and time as a smooth, continuous fabric. Quantum theory insists everything is pixelated at the tiniest scales. Imagine trying to zoom in on a digital photo until you hit individual pixels. That's the Planck length, the smallest meaningful unit of space. At this level, the idea of a zero-volume, infinitely dense singularity becomes nonsense. Theories like loop quantum gravity take this idea and run with it, proposing that singularities aren't points of infinite collapse but bounces, where matter reaches maximum compression and rebounds like a spring. Picture a black hole's core not as a dead end, but as a cosmic trampoline, hurling energy back out in a new form. String theory offers another escape route, suggesting singularities might be smeared across hidden dimensions or dissolved into vibrating strings so tiny they blur the line between particle and wave. Even Hawking radiation hints at a way out, with black holes slowly leaking energy and information over eons, avoiding the need for infinite density altogether. But the boldest idea comes from holographic principles, which argue that singularities are illusions, projections of information encoded on the black hole's event horizon, like a three-dimensional movie rendered on a two-dimensional screen. The stakes couldn't be higher. If singularities are real, they're cosmic guillotines chopping off predictability and leaving us with gaps in the story of the universe. But if they're just artifacts of incomplete theories, solving this paradox could unlock quantum gravity, the holy grail of modern physics. It's a race to rewrite the rules of reality, where the prize isn't just understanding black holes, but finally seeing the universe with both eyes open. After all, if infinity exists anywhere, it's not in the stars or the void, but in the human mind's refusal to accept "we don't know" as the final answer. Stretch out a map of the cosmic microwave background, the faint afterglow of the Big Bang, and you'll notice something peculiar. No matter which direction you look, the temperature of the universe is almost identical, varying by less than 1 part in 100,000. This uniformity is a cosmic mystery because, according to the speed of light, distant regions of the early universe couldn't have exchanged heat or information. It's like walking into a concert hall where every seat is magically the same temperature, even though the people in the front row and the back row never had time to pass a single whisper between them. This is the horizon problem, a paradox that forces us to ask, how did the universe coordinate itself so perfectly? The leading solution is cosmic inflation, a theory proposing that the infant universe underwent a sudden, exponential growth spurt, ballooning from smaller than an atom to the size of a grapefruit in a fraction of a second. This explosive expansion would have smoothed out temperature differences like stretching a wrinkled sheet of fabric until every crease vanishes. But here's the catch: inflation doesn't explain why it happened. What triggered this runaway expansion, and why did it stop? It's as if we've found the answer to how, but are left staring at a deeper why, like uncovering a machine without an instruction manual. Some theorists argue that inflation might not be the only answer. Bouncing cosmologies suggest our universe wasn't born from a singularity, but emerged from the collapse of a previous cosmos, like a phoenix rising from its own ashes. In this scenario, the pre-Big Bang universe could have had enough time to reach equilibrium before contracting and rebounding, carrying that smoothness into our current cycle. Others turn to holographic principles, where the universe's three-dimensional structure is actually a projection of information encoded on a two-dimensional surface. If true, the horizon problem might be an illusion, a trick of perspective, like realizing the shadow on your wall is just a hand puppet held up to the light. The most unsettling possibility, that our universe's uniformity isn't a coincidence but a clue to something far stranger. If multiple regions of space-time were stitched together in the early cosmos like patches on a quilt, their edges might have blended seamlessly, leaving no trace of the seams. Or perhaps the laws of physics themselves were different at the beginning. allowing for instantaneous connections that now seem impossible. Whatever the answer, the horizon problem isn't just about temperature. It's a window into the universe's first moments, a puzzle that challenges us to rethink not just how the cosmos began, but what beginning even means. Every time we measure that near-perfect microwave glow, we're peering back at a mystery written in the faintest ink, waiting for us to decode it. Magnets are everywhere, from fridge decorations to the inner workings of your smartphone, and every one of them has two poles, a north and a south. Break a magnet in half and you don't get isolated poles, you just create two new magnets, each with its own pair. But what if the universe wasn't so symmetrical? What if there were particles carrying just a single magnetic charge, wandering through space like cosmic loners? These hypothetical entities, called magnetic monopoles, aren't just a fun thought experiment. They're a glaring prediction of grand unified theories, the frameworks that aim to stitch together all fundamental forces. Yet, despite decades of searching, not a single monopole has ever been detected. This is the magnetic monopole paradox, a ghostly absence that haunts modern physics. The math is undeniable. When the universe was a seething soup of energy just fractions of a second after the Big Bang, the conditions were perfect for monopoles to form in staggering numbers. Grand unified theories suggest these particles should have been as common as protons, littering the cosmos with their distinctive signatures. Fast forward to today, and we'd expect to find at least one monopole in every volume of space the size of a sugar cube. But our detectors remain silent, so where did they all go? One compelling answer lies in cosmic inflation, the same rapid expansion that solved the horizon problem. If the universe ballooned exponentially in its earliest moments, it could have stretched monopoles so thin that they're now impossibly rare, like a single grain of sand lost in a desert the size of a galaxy. This would explain their absence, but it raises another question. Why didn't any survive? Even inflation shouldn't have erased every last one. Some theorists speculate monopoles might be hiding in plain sight, trapped in cosmic strings, exotic filaments of space-time left over from the early universe. Picture a necklace where the beads are monopoles, strung along invisible threads woven into the fabric of reality. Others argue the paradox hints at something deeper, that grand unified theories are missing a crucial piece. Maybe monopoles were never created because the early universe took a different path, skipping the phase where they'd naturally emerge. Or perhaps they decayed into other particles almost instantly, leaving behind only faint echoes in the quantum foam. There's even a wild possibility that monopoles aren't particles at all, but temporary disturbances in quantum fields, flickering in and out of existence too briefly to catch. The search isn't over. Experiments like Mo-Edel at the Large Hadron Collider hunt for monopoles by scouring particle collisions for traces of their unique magnetic fingerprints. Others scan ancient minerals for damage trails left by monopoles passing through Earth over billions of years. Every null result tightens the noose around our theories, forcing us to ask whether we're wrong about unification, inflation, or even the birth of the cosmos itself. The magnetic monopole paradox isn't just about missing particles, it's a litmus test for our understanding of the universe's deepest symmetries. If monopoles exist, they'd rewrite textbooks. But if they don't, their absence might be the clue that leads us to an even grander theory, one where the cosmos plays by rules we've yet to imagine. Either way, the hunt for these elusive loners proves a timeless truth. Sometimes what we don't find teaches us more than what we do. According to our best theories, the Big Bang should have created equal amounts of matter and antimatter particles and their mirror opposites, destined to collide and annihilate in bursts of pure energy. Yet here we are, surrounded by galaxies, planets, and life, all built from matter with hardly an antimatter atom in sight. This staggering imbalance is the Baryon Asymmetry Paradox, and it's not just a quirk of physics, it's the reason anything exists at all. The mystery runs deep. Every experiment we've conducted shows that matter and antimatter are nearly perfect twins, obeying the same laws with only the tiniest differences. When they meet, they vanish in a flash of gamma rays, leaving nothing behind. So why didn't the universe cancel itself out moments after birth? The answer might lie in a subtle cosmic favoritism called CP violation, a phenomenon where particles and their antiparticles don't always behave as perfect mirrors. In the 1960s, physicists observed this asymmetry in kaons, exotic particles that decay slightly differently than their antimatter counterparts. It was a breakthrough, but here's the catch. The effect is far too weak to explain the overwhelming matter surplus we see today. It's like finding a single grain of sand when you expected a beach. Theorists have proposed wilder mechanisms to fill the gap. Leptogenesis suggests that ghostly neutrinos, particles so elusive they pass through lead like it's air, might hold the key. In the early universe, these neutrinos could have decayed unevenly, producing a tiny excess of matter that snowballed into the cosmos we know. Other models point to phase transitions in the infant universe, where space itself briefly became a supercooled soup, separating matter and antimatter like oil and water. Imagine the universe as a bottle of soda suddenly shaken. Bubbles of matter formed while antimatter fizzled away, leaving behind the universe's structural backbone. But the boldest idea comes from quantum gravity. If singularities in black holes or the Big Bang itself can warp the rules of reality, perhaps they also tweak the scales in matter's favor. Picture a cosmic casino where the house always wins, except here, the house is the fabric of space-time, subtly rigged to let matter dominate. The stakes couldn't be higher. Solve this paradox, and you've unlocked not just the origin of atoms, but the origin of existence itself. Every star, every planet, every breath you take hangs on this razor's edge between something and nothing. And that's the real wonder. The universe didn't have to be this way. It could have been a blank slate, a void without form. Instead, we're left with a cosmos that chose to be here, and a paradox that keeps us asking why. The universe isn't just expanding, it's accelerating, racing outward faster with every passing moment, as if some unseen hand is pressing harder on the cosmic gas pedal. This baffling discovery, which earned a Nobel Prize in physics, points to a mysterious force we call dark energy. Yet here's the catch. While dark energy makes up a staggering 68% of the universe's total content, we have no idea what it actually is. It's like living in a house where most of the rooms are locked and the keys have vanished into thin air. The simplest explanation ties dark energy to the vacuum of space itself, a cosmic backdrop that, according to quantum physics, should be fizzing with energy. But when we calculate how much energy the vacuum ought to have, the numbers are catastrophically wrong. Theory predicts a value 10 raised to the power of 120 times larger than what we observe. It's the equivalent of expecting a tsunami and finding barely a ripple. This mismatch, known as the cosmological constant problem, is the largest discrepancy between prediction and reality in all of science. If the vacuum energy were even slightly stronger, galaxies would have been torn apart before they could form. Slightly weaker, and the universe would have collapsed in on itself eons ago. The fact that we exist at all suggests dark energy's density is fine-tuned to an almost impossible degree, a cosmic coincidence so precise it defies belief. Some theorists argue that dark energy isn't a static property of space but something dynamic, like an evolving field slowly gaining strength over time. Quintessence, one such proposal, imagines dark energy as a fluid that permeates the cosmos, its pressure and density shifting as the universe ages. Picture a balloon that starts inflating slowly, then suddenly surges as if filled with an invisible breath. But even this elegant idea struggles to explain why the energy density is so vanishingly small, unless there's some undiscovered symmetry or cancellation mechanism hiding in the math. Then there's the radical possibility that dark energy isn't energy at all, but a sign that Einstein's theory of gravity breaks down on cosmic scales. Modified gravity theories like Mund's galactic cousin suggest that what we perceive as acceleration might actually be gravity behaving differently over vast distances. It's as if we've been reading the universe's equations in a language we only half understand, mistaking a grammatical quirk for a fundamental truth. The most unsettling implication of the dark energy paradox isn't just our ignorance, it's the timeline it imposes. If dark energy remains constant, the universe will expand forever, galaxies drifting apart until the night sky goes dark. If it grows stronger, space itself might eventually rip apart in a big rip, shredding atoms in the final moments of existence. Yet despite these apocalyptic possibilities, dark energy remains a shadow on the edge of our understanding, a reminder that the universe's greatest mysteries aren't just in the stars, they're woven into the empty space between them. And perhaps that's the most humbling lesson of all, that the force shaping the fate of everything might forever lie just beyond our grasp, a cosmic riddle written in the void itself. Zoom in far enough on the fabric of reality, and you'll reach a point where the universe itself seems to glitch, a scale so small, it makes atoms look like galaxies. This is the Planck length, roughly 1/1,000,000,000 of a trillionth the size of a proton, where space and time should dissolve into a seething quantum foam. According to our best theories, at these unimaginably tiny distances, gravity becomes so wild it warps space-time into chaotic fluctuations, like a stormy ocean churning with microscopic whirlpools. But here's the paradox: we still describe space-time as smooth and continuous all the way down to zero. How can both these ideas be true? The Planck length isn't just a number, it's a boundary where physics as we know it collapses. Imagine trying to measure the coastline of a beach with a ruler shorter than the grains of sand. At some point, the very idea of distance loses meaning. Similarly, below the Planck length, quantum gravity should twist spacetime so violently that concepts like here and there become nonsensical. Yet our equations stubbornly treat spacetime as a flawless mathematical sheet, infinitely divisible. This contradiction isn't just a technical hiccup, it's a flashing warning sign that we're missing something profound about reality's building blocks. One tantalizing solution is that spacetime might be pixelated, like a digital image made of tiny, indivisible dots. Loop quantum gravity paints this picture, suggesting space is woven from finite loops or atoms of geometry. Think of it as a cosmic tapestry where threads can't be split further no matter how sharp your scissors. In this view, the Planck length isn't a limit of our tools, but a fundamental feature of the universe, like the smallest possible stitch in the fabric of existence. But there's a twist. If spacetime is discrete, how does it appear so seamless to us? The answer might lie in emergence, the idea that smooth space is an illusion, a collective effect of countless quantum interactions, like the surface of water appearing solid until you peer at its molecules. String theory takes this further, proposing that what we call space could be a hologram, a projection from a deeper, hidden dimension where the true rules are written. The Planck length paradox doesn't just challenge our theories, it forces us to confront whether space and time are even real at the most basic level. Are they the stage or just part of the play? Until we crack this riddle, the universe remains a puzzle with pieces we're only beginning to recognize, and the smallest of them might hold the biggest secrets. Crossing the event horizon of a black hole should be uneventful, at least, according to Einstein's general relativity. Infalling astronauts wouldn't feel anything special as they passed this point of no return, drifting smoothly toward their doom. But quantum mechanics paints a far more violent picture, a blazing wall of high-energy particles lurking just beyond the horizon, ready to incinerate anything that gets too close. This is the black hole firewall paradox, a cosmic tug of war between two foundational theories, each insisting the other must be wrong. The trouble starts with Hawking radiation. As pairs of virtual particles pop in and out of existence near the horizon, one can fall in while the other escapes, stealing a tiny bit of the black hole's energy. Over time, this process should cause the black hole to evaporate entirely. But here's the catch: quantum mechanics demands that information can never be truly lost. If the escaping particles carry no trace of what fell in, the rules of quantum physics break down. To preserve information, theorists propose that the outgoing radiation must be entangled with particles inside the black hole, but this creates another problem. Quantum entanglement is monogamous. A particle can't be entangled with both its partner outside the horizon and the infalling matter simultaneously. Something has to give. Enter the firewall, a proposed solution where the entanglement snaps violently at the horizon, releasing enough energy to create a searing barrier. It's as if the universe erects a "keep out" sign made of pure radiation, burning away the paradox at the cost of relativity's smooth passage. But this raises eyebrows. Why would space-time, which curves gently everywhere else, suddenly turn into a cosmic bonfire at the horizon? It's like walking through a door only to find the frame is made of lava. Some physicists argue the firewall is a red herring, a sign we're missing a deeper principle. Black hole complementarity suggests there's no contradiction because the infalling observer and the outside watcher can't compare notes. Their experiences are equally valid but mutually exclusive, like two sides of a coin that can never be seen at once. Others propose modified horizon physics, where quantum effects subtly alter the event horizon's nature without creating a firewall. Think of it as a holographic veil. What looks like a deadly barrier from one perspective is just a data processing layer from another. The firewall paradox isn't just about black holes, it's a proxy war for the soul of physics. Every proposed solution forces us to bend or break rules we once thought unshakable. And until we find the right path, the event horizon remains the ultimate cosmic tightrope, where one misstep could send our theories tumbling into the abyss. The act of looking at something shouldn't change it, yet in the quantum world, observation isn't passive. It's an intervention, a ripple that collapses delicate superpositions into definite states. This is the observer effect paradox, a quirk of quantum mechanics so profound it blurs the line between the seen and the seer. Imagine a spinning coin hovering between heads and tails until you catch it mid-air, only then does it choose a side. But here's the unsettling question: what counts as an observation? Does it require a conscious mind, a machine, or just any interaction with the environment? The answer could redefine what we call reality. Decoherence theory offers one compelling explanation. When quantum systems interact with their surroundings, whether a photon hitting a detector or a stray air molecule bouncing off an atom, their fragile superpositions leak into the environment, spreading so thin they appear classical. Think of it like ink dropped into a turbulent river. The colors don't vanish, but they become impossibly diluted, leaving the water looking clear. This process explains why we don't see quantum weirdness in everyday life, but it dodges the deeper issue. At what point does this interaction qualify as a measurement? A single photon striking a camera sensor might not collapse a wave function, but a billion surely would. The boundary remains frustratingly fuzzy. The Copenhagen interpretation takes a bolder stance, declaring that measurement requires a classical apparatus, a device or observer outside the quantum system. But this just kicks the paradox up a level. If everything is made of quantum particles, how can anything be truly classical? It's like building a castle on clouds, each layer relying on the one below until the foundation dissolves into mist. Some physicists, like Eugene Wigner, argued that consciousness itself might be the ultimate arbiter, a notion that bridges physics and philosophy but leaves labs grappling with how to test such an idea. Meanwhile, the many worlds interpretation sidesteps the problem entirely. Instead of collapsing, every possible outcome branches into a parallel universe, turning observation into a cosmic fork in the road. You measure an electron spin, and the universe splits, one where you record up, another down. No mysterious collapse, no privileged observers, just an ever-expanding multiverse where all possibilities play out. Yet this raises its own questions. Why do we perceive only one outcome, and where do these branches physically reside? The most radical perspective comes from cubism, which treats quantum states not as objective realities but as personal beliefs, tools for prediction rather than description. In this view, the observer isn't disturbing some external truth. They're updating their own expectations based on interactions. It's as if the universe is a vast game of probability, and measurement is simply placing a bet. The observer effect paradox doesn't just challenge how we do science, it forces us to confront what science is even about. Are we uncovering an independent reality, or co-creating it through the very act of looking? Every quantum experiment whispers the same unsettling possibility, that the universe might not exist in a fixed state until we ask it to. And if that's true, the biggest mystery isn't in the particles, it's in the act of seeing them at all. Time crystals sound like something ripped from a science fiction novel, structures that pulse and oscillate forever without any energy input, like a pendulum that never stops swinging. But these aren't theoretical fantasies, they're real, and they defy one of the most sacred laws of physics, the second law of thermodynamics, which states that systems inevitably trend toward disorder. So how can time crystals exist without violating the rules of the universe? The answer lies in the bizarre world of quantum many-body systems, where particles don't just interact, they dance in perfect, self-sustaining harmony. At first glance, time crystals seem like perpetual motion machines, a concept long dismissed as impossible. But there's a crucial difference. Perpetual motion would require energy to be created from nothing, while time crystals operate in a state of quantum suspension. Imagine a group of atoms arranged in a repeating pattern, not just in space, but in time, flipping between two configurations indefinitely, like a cosmic metronome ticking without a wind-up. This isn't motion in the traditional sense. It's a delicate quantum waltz where particles are entangled in such a way that their collective state cycles predictably without losing energy. The breakthrough came when researchers realized that time crystals don't exist in equilibrium. They're inherently out of balance, stabilized by quantum coherence rather than external forces. Think of them as a ball resting not at the bottom of a valley, but on a knife's edge, perfectly balanced between two states. Even more astonishing, they were first created not in some high-energy lab, but in humble tabletop experiments using chains of ions or diamond defects, their rhythmic pulses detected with laser light. But here's the paradox. If time crystals don't consume energy, why don't they violate thermodynamics? The secret is in the fine print. While their internal structure cycles endlessly, they can't do anything with that motion. no work is extracted, no energy is transferred. It's like a clock that ticks forever but can't power itself. This loophole keeps them compliant with the laws of physics, even as they stretch our understanding of what motion really means. The implications are staggering. Time crystals could revolutionize quantum computing, acting as ultra-stable memory cells immune to decoherence. Or they might hint at deeper truths about time itself, suggesting that under the right conditions, the arrow of time isn't just a one-way street, but a spiral, looping back on itself in perfect, eternal rhythm. Yet the most tantalizing question remains: are time crystals a quirk of carefully controlled experiments, or do they exist naturally in the wild? Some theorists speculate they could form in the extreme conditions of neutron stars or even the early universe, hiding in plain sight until we learn how to look. Whether lab-made or cosmic, time crystals force us to rewrite the textbook on what matter can do, proving once again that the universe's strangest ideas often start as impossibilities until they're not. The universe as we know it might be nothing more than an illusion, a three-dimensional projection painted onto a distant, two-dimensional surface like a cosmic hologram. This is the holographic principle paradox, an idea so radical it suggests space-time itself isn't fundamental, but emerges from something far stranger: information encoded at the edges of reality. Picture a movie screen where the images appear to leap into the theater, full of depth and motion, except here, the screen is the boundary of the universe, and the movie is everything you've ever touched, seen, or been. But how can the richness of our 3D world, the swirl of galaxies, the curve of a planet, the warmth of sunlight, be stored on a flat, distant wall? The answer could rewrite physics as we know it. The paradox traces back to black holes, those cosmic information shredders. When matter falls into a black hole, its details seem lost forever, violating quantum mechanics' insistence that information can't be destroyed. But in the 1990s, physicist Leonard Susskind and others proposed a wild solution. What if the information isn't lost but smeared across the black hole's event horizon, like ink on a stretched balloon? This led to a broader realization: if a black hole's interior can be described entirely by data on its surface, maybe the entire universe works the same way. Imagine your brain storing memories not in 3 dimensions, but as flat patterns on your skull. It's a staggering trade-off: depth for data, volume for code. Yet the math checks out. In a holographic universe, the information needed to describe every particle, every force, every moment of time fits perfectly onto a bounding surface 1 dimension lower. It's like compressing a library into a single bookshelf, where each book contains not just words, but the blueprint for an entire world. String theory lends weight to this idea, suggesting that the vibrations of tiny strings, the building blocks of reality, might actually be shadows of interactions happening on a distant, flat plane. But here's where the paradox bites. If reality is a hologram, why does it feel so solid? Why do we experience space as expansive and time as flowing, if both are just elaborate decodings of 2D data? One clue comes from entanglement, the quantum phenomenon where particles remain connected across vast distances. Some theorists argue that space-time itself might be woven from these threads of entanglement, like a tapestry whose stitches are quantum links. Picture a 3D image emerging from a million tiny pixels, not by magic, but by the way those pixels relate to one another. The implications are dizzying. If the holographic principle is true, then black holes aren't just cosmic oddities. They're Rosetta Stones for deciphering the universe's true language. The Big Bang might not have been the birth of space and time, but the moment a lower dimensional system rendered our 3D reality. Even gravity could be an emergent force, a side effect of information processing at the cosmic edge. Yet the biggest question remains unanswered. Where is the screen? Is it the edge of the observable universe, an abstract mathematical boundary, or something beyond our current comprehension? The Holographic Principle paradox doesn't just challenge our understanding of reality, it forces us to ask whether reality is even the right word. After all, if the universe is a projection, who or what is holding the projector? The standard model of particle physics is one of humanity's greatest intellectual triumphs, a framework so precise it can predict the behavior of subatomic particles with breathtaking accuracy. Yet there's a ghost in this machine, the neutrino, an elusive particle that slips through matter like a whisper through a crowded room. For decades, physicists assumed neutrinos were massless, flitting through the cosmos at the speed of light without leaving a trace. But nature had other plans. Experiments revealed that neutrinos do have mass, just an impossibly tiny amount, a feather's weight compared to the smallest known particles. This discovery upended decades of theory, exposing a crack in the standard model so glaring, it demands an entirely new chapter of physics. The mystery deepens when you ask how neutrinos acquire mass. Unlike electrons or quarks, which get their heft from interactions with the Higgs field, neutrinos seem to play by different rules. They might not even be their own antiparticles, a possibility that opens the door to so-called sterile neutrinos, hypothetical particles that interact with nothing except through gravity. Imagine a shadow world of matter, invisible and intangible, yet subtly tugging on the fabric of reality. These phantom particles could explain neutrino oscillations, the bizarre phenomenon where neutrinos switch identities mid-flight, morphing between three known types like cosmic chameleons. But sterile neutrinos aren't the only solution. Some theorists argue that neutrino mass hints at extra dimensions, tiny, curled-up layers of space where particles gain properties we can't perceive directly. Picture a guitar string vibrating in higher dimensions. The notes it plays in our 3D world might just be echoes of a richer, hidden symphony. Others propose seesaw mechanisms where ultra-heavy partner particles balance the neutrino's feather-like mass, leveraging scales so extreme they dwarf anything we've detected in colliders. The stakes couldn't be higher. If neutrinos break the standard model, they might also hold the key to one of cosmology's biggest puzzles: why the universe is made of matter at all. The same quirks that give neutrinos mass could explain how a tiny excess of matter survived annihilation with antimatter in the Big Bang's aftermath, seeding everything we see today. It's as if these ghostly particles are cosmic scribbles in the margin of physics, notes from a deeper theory we've yet to decipher. Every experiment hunting neutrino mass, from underground detectors filled with liquid argon to telescopes scanning for distortions in the cosmic microwave background, isn't just probing a particle. They're chasing the outline of a larger truth, one where the rules we know are just the first stanza of a much grander song. And until we solve this paradox, the neutrino remains both a question and a clue, whispering secrets from the edge of understanding. Black holes are cosmic enforcers, wrapping their singularities points of infinite density in the protective cloak of an event horizon. But what if nature isn't so meticulous? What if singularities could exist naked, exposed to the universe without their dark shrouds? This is the cosmic censorship paradox, a challenge to one of relativity's most cherished assumptions, that singularities must always be hidden, never laid bare. Roger Penrose first proposed this idea as a cosmic law, arguing that gravity itself would always curtain off these mathematical monstrosities. Yet decades later, we still don't know if the universe follows that rule, or if it allows reality to tear open in plain sight. The paradox isn't just theoretical, If naked singularities exist, they'd unleash chaos on physics. Event horizons act as cosmic firewalls, shielding the outside universe from the unpredictable madness at a singularity's core. Remove that barrier, and the equations of general relativity spiral into nonsense, spitting out answers that change depending on how you look at them. It's like trying to predict the weather in a world where the laws of physics rewrite themselves by the second. Even worse, without an event horizon, a naked singularity could radiate unpredictable bursts of energy or warp space-time in ways that ripple backward through time. Picture a crack in the universe's foundation, one that doesn't just break the rules but sets them on fire. So why hasn't nature banned these cosmic rule breakers? Some simulations suggest that under extreme conditions like the collision of two black holes or the collapse of certain exotic stars, a singularity might briefly escape its horizon before gravity slams the door shut. Others argue that quantum effects could stabilize naked singularities, like microscopic flaws in a diamond that somehow make it stronger. Then there's the radical possibility that cosmic censorship isn't a law but a suggestion that the universe occasionally lets its guard down, leaving singularities exposed in regions where no one's looking. Yet the most unsettling implication isn't about black holes, it's about predictability, the bedrock of science. If naked singularities roam the cosmos, even in secret pockets of space, they'd render the future fundamentally unknowable. A single exposed singularity could send shock waves of uncertainty through the fabric of causality, making it impossible to calculate what happens next, no matter how advanced our math. It's a paradox that doesn't just test our theories, it asks whether the universe plays fair. And until we find proof one way or another, we're left wondering, is reality a well-ordered courtroom, or a courtroom where the judge sometimes takes off their robe? A watched pot never boils, or so the saying goes. But in the quantum world, this old adage takes on a terrifyingly literal meaning. The quantum Zeno paradox suggests that simply observing a system often enough can freeze it in place, like hitting pause on reality itself. Named after the ancient Greek philosopher's arrow paradox, where motion becomes impossible if time is divided into ever smaller slices. This quantum version reveals how measurement doesn't just reveal reality, it actively shapes it. At the heart of this paradox lies a startling experiment. When unstable particles are monitored continuously, their decay slows dramatically. It's as if the particles, aware of being watched, cling to their original state out of sheer quantum stage fright. This isn't just a laboratory curiosity. Physicists have used this effect to stabilize qubits in quantum computers, essentially hacking time by bombarding them with observations. But here's the rub. In quantum mechanics, observation doesn't require a conscious observer. Any interaction with the environment, a stray photon collision, or even the whisper of a magnetic field can count as a measurement, nudging the system toward a definite state. The implications ripple through the foundations of physics. If frequent observations halt change, does that mean time itself is a byproduct of our inattention? Some interpretations suggest that without measurement, quantum systems evolve smoothly like waves, but the act of looking forces them to choose a particle-like state, resetting their evolutionary clock. Picture a game of musical chairs where every glance freezes the players in place, stretching moments into eternities. Yet the paradox deepens when we ask why this happens. The Copenhagen interpretation treats wave function collapse as axiomatic, a brute fact of nature, while the many worlds view sidesteps collapse entirely, arguing that all outcomes still occur in branching realities. But the Zeno effect hints at a middle ground. That measurement isn't a binary switch between wave and particle, but a spectrum of disturbance. The more you probe, the more you disrupt. Practical applications abound. In medicine, radioactive tracers used in PT scans could theoretically last longer under observation, while atomic clocks might achieve greater precision by mitigating quantum jumps. But the true revolution lies in philosophy. The Zeno paradox forces us to confront whether time flows at all, or if it's stitched together from countless tiny pauses, like frames in a film reel where the projector is our own gaze. Perhaps the greatest irony, the more we try to observe time's true nature, the more we might be stopping it in its tracks. In the quantum realm, watching isn't passive, it's participation. And that leaves us with a haunting question. If a tree falls in a quantum forest with no one to measure it, does it ever really fall at all? From the silence of alien civilizations to the fiery fate of black holes, these 29 paradoxes aren't just scientific puzzles, they're cosmic breadcrumbs, leading us deeper into the universe's greatest unsolved mysteries. Each one tears at the seams of our understanding, revealing gaps so profound they've spawned entirely new branches of physics. Take the Fermi Paradox, which forces us to confront whether intelligence is fleeting or if the universe is hiding something from us. Or the black hole information paradox, where the clash between quantum mechanics and relativity suggests our theories are missing a crucial piece of the puzzle. These aren't just abstract thought experiments, they're urgent calls to rethink reality itself. What makes these paradoxes so powerful is how they transform ignorance into inspiration. The vacuum catastrophe, with its embarrassing mismatch between prediction and observation, isn't a failure, it's a beacon, guiding physicists toward undiscovered principles that might unite quantum fields and gravity. The simulation paradox doesn't just question whether we're living in a virtual world. It challenges us to define what a real even means. And the Boltzmann brain, with its unsettling suggestion that we might be fleeting glitches in the void, pushes us to ask why the universe feels so ordered in the first place. Every paradox is a fork in the road where science must choose between doubling down on old ideas or venturing into the unknown. But here's the beautiful irony: the more we learn, the stranger the cosmos becomes. Solving one paradox often reveals another, like peeling an infinite onion. Dark energy's acceleration of the universe led us to question the nature of empty space. The holographic principle turned black holes into Rosetta Stones for decoding spacetime itself. Even Olbers Paradox, born from a simple question about the night sky's darkness, helped cement the Big Bang theory. These aren't dead ends, they're doorways, each one inviting us to step further into the mystery. So which paradox grips you the most? Is it the eerie silence of the Fermi Paradox, the existential whiplash of the simulation argument, or the quantum roulette of the observer effect? Drop your thoughts in the comments. We're all detectives in this grand cosmic mystery together. And if your brain isn't thoroughly twisted yet, hit subscribe. The universe has plenty more enigmas waiting, and we're just getting started. After all, the greatest paradox of all might be this: the more we uncover, the more we realize how much wonder is left to explore.